And today I want to talk about the most important dimension reduction technique there is, namely principal component analysis. That and its relation to SVD, that's the singular value decomposition. Who has studied the SVD before? One, okay. And then I want to spend a lot of time on a pretty abstract level, so talking about the role of bilinear decompositions, of which PCA is one example, in unsupervised learning. And then we can become more specific again, and depending on our mood, we will do either something lighter or we will talk about probabilistic Pca and probabilistic latent semantic analysis. Okay, Pca first. So note my spelling. It is principal with AL and not principle as in something that you uphold as a guiding line of how to live life. I'm saying that because there are so many papers even where it's misspelled, but it's principal with an AL. So the motivation of using PCA, or the thing that makes it work, is that real data does not completely fill high-dimensional space, where fill is quote unquote. So in more technical terms, I will say that the nominal dimensionality is not the same as the intrinsic dimensionality. Given that I've not defined either term, I can always state that. So nominal dimensionality is simply the number of measurements that you have for each object. So it was the number p on the previous slide. The intrinsic dimensionality is that part of space which is actually filled in some sense by the observations. So I'll try and show you one picture. Sorry, this is in German. So I'm looking at this here. We have a couple of points here, and the points in the box are really three-dimensional. Then we have points scattered in a plane, those are two-dimensional. And then we have points scattered along this line or along this circle, where it's locally one-dimensional, except at this intersection where the intrinsic dimension is a little bit higher. So the exact intrinsic dimensionality, you know, us humans, we intuitively segment this object into several parts. We would say the intrinsic dimensionality here is 3, and there it is 2, and there it is 1. And at this point we can argue, you know, maybe it's 1.5 or something larger than 1, something smaller than 2. Now, estimating this from data, in particular from noisy data, is of course much harder, especially if it's you know, not if it cannot be segmented as nicely as the data that I've shown you here. However, the main point here is that this is a three-dimensional feature space, and even the points here or there in this toy example, I still need 3 measurements to specify their position. I still need 3 features, so the nominal dimensionality is still 3, but the intrinsic dimensionality is smaller. Now you also see that in the intrinsic dimensionality, it really is a function of space, but you know, for starters, you can go ahead and try and estimate a global intrinsic dimensionality. And because estimating shapes like this from few scattered points, especially in high dimensions, is hard, we need simpler assumptions, and the simplest assumption that you could make is to say that your points live on a linear subspace. So that's what PCA tries to do. It tries to find a linear subspace that best fits your data. And I still need to specify what exactly I mean by best. If we can do this, we have a couple of uses. So, for instance, well, we can use it simply for compression by giving only the coordinates in the linear subspace rather than the full coordinates. This can be useful for looking at data, or you can use this as a dimension reduction step, as a pre-processing for supervised learning. In general, this is a technique from unsupervised learning. So compression, visualization, or dimension reduction, we're not talking about labels here at all. So this is unsupervised learning. As regards visualization, I have a picture somewhere. Could you show this, please? So those are the MNIST digits that you already know from the exercises. Each digit, if we forget about the fact that this is a number and we can look at it, is a sample with how many dimensions did you use? Is it 128 or? Okay, 7. So each point, the nominal dimensionality of this is 768. You have 768 measurements for each digit. Now, luckily, we can plot it. We could plot each example simply as an image and look at it, the way we do. But if this is some data that cannot be looked at in terms of an image, so let's say these are patients and you have 768 measurements for each of them, you would still like to see if if there's any kind of structure, if you can somehow group it. And here's an example of a 2D subspace, so a plane that was fitted to this 768-dimensional cloud of points. And now the coordinates for each observation are simply given in this 2D subspace, in the 2D plane. In addition, you see colors here, and the colors simply code for the numbers. So the coding that you see here in terms of numbers and the colors is redundant, is not used by PCA because it's unsupervised learning. So we are not we're not using the labels at all in producing this plot. However, if one doesn't have labels, this can still be interesting to see if there's perhaps any cloud of points that is localized or that's separated a bit from the others. Or if you do have labels, you can use them to color code your examples like it has been done here, just to see if there's, in a low dimensional projection, if there's any meaningful structure left. If not, that doesn't tell you that supervised learning doesn't work. Remember, these are only 2 dimensions, and I could very well imagine a decision boundary that perfectly separates the points in a higher dimension, but not in 2 dimensions. So it is not terribly informative, but it's better than not looking at your data at all. So if you get a hard disk full of data and if you cannot look at them in terms of images, it's a good idea to make plots like these. And we will see better visualization techniques towards the end of the semester. So what do we want to do? We have a set of points. So let me argue that now my nominal dimensionality here is 2, and I now want to fit a 1-dimensional linear subspace, also known as a line, to these points. Now that may remind you of linear regression. It is almost not quite the same. So let me zoom into this area here. What you do in linear regression is that you minimize the sum of squares, where the squares are only measured in the vertical direction. If we have a coordinate system with x and y, then in linear regression you assume that there's no error whatsoever in your measurements x, but only error in the measurements, in the labels y, and this is why you minimize these vertical distances that I've indicated here. Now in Pca, so the red line was regression, linear regression, and the green line now is principal component analysis. In principal component analysis, you really minimize the orthogonal distances. So you project your points orthogonally onto the subspace, and actually there are now two views. We can either say that Pca minimizes the sum of these orthogonal distances, actually the squares minimize the sum of the squared orthogonal distances, or Pca maximizes the spread of your data within the low-dimensional subspace. So let's say I have a Pca line, my first principal component plotted here, and to make things simpler, let's assume that you have subtracted the mean. So after subtracting the mean, my center of mass will go right through my cloud of points here, or my principal component will go through the origin. So this was feature 1 in this feature space, and this was feature 2. And feature 1 and feature 2, unlike in the regression case where we say that one of them is without error, we now treat them in a symmetric fashion. So feature 1 and feature 2 have the same rights and obligations. Now, if you look at any point now, you can see that I can decompose it. Let's look at this point here. I can write this as a sum of two vectors, namely as a vector that lies within my linear subspace and a vector that is orthogonal to this linear subspace. I can use that same decomposition for each and every point, and to now find the first principal component, I can either say that I want to make the spread within the subspace as large as possible, so the sum of the variances of these points within the subspace would be as large as possible, or I want to make the residuals, these orthogonal parts, as small as possible. These are two views of the same thing, and they lead to the same result. So let's do this in equations. So I will assume that the mean has been subtracted already. So that I can write my matrix x times, this was the vector of ones. I'm writing it out again. Should be 0. So I'm again using the convention that X is a matrix holding all my observations. I have n observations, each of which are p-dimensional, and I collect them in a matrix with p rows and n columns. And this is a vector here which has n rows and just one column, and then this thing here is p by 1. So my center of mass should be the 0 vector. And I'm now taking the view where I want to approximate my data as well as possible. So I want to find the subspace. I will start with a one-dimensional subspace described by this vector W, such that my original observations have maximal spread in this subspace. So I can say I write W transpose X. Let's again look at the dimensions here. This is a 1 by P vector giving my first basis vector. X was P by N. So what I get is the coordinate in this new, I obtain for each observation a number telling me, a single scalar number telling me where in the subspace it lies. And now I'm taking all these numbers and squaring them and adding them up. Now if I want to maximize this, I could make it arbitrarily large by simply letting W grow. But I want to figure out only the direction of W while restricting it to unit norm. Okay, and I can rewrite that. As follows. So this is a 1 by n vector. So I can take that and multiply it with its transpose. And I still have this constraint. Or I can write that in a Lagrangian form. And I'm sorry, this should be minus here. And it's messy, so I'm writing this again. This is a lambda, my Lagrange multiplier. Okay. And this is now my Lagrangian here. I should eliminate the argmax here. Sorry, I've miswritten this. And I'm now looking for an extremum, so I'm differentiating my Lagrangian with respect to W, which is a vector. So we have a scalar number, and I'm differentiating the scalar number with respect to a vector. And if you do that, you again obtain a vector. Okay, so this is I have a vector here of W1, W2, and so on up to WP. My numerator is a scalar number, and if I'm differentiating a scalar number with respect to a vector, I will obtain P responses, which I can again stack as a vector. So, in case you haven't seen that before, convince yourself that the derivative I'm writing down here is going to be correct. Okay, and I want this to be an extremum, so I set my first derivative to 0. And I can then solve, or I get the following eigenequation. So we have an eigenvalue problem. And if I now solve this, then my solution W will give my first principal component. Well, and this may have multiple eigenvalues, so I'm looking for the largest one. So we have found the one-dimensional subspace that I want to use to fit my data. So in the example we had seen here, I would already be done. So W would be a unit vector. The sign is not defined, but it would be a unit vector along, or I'm writing W1 now, it would be unit vector along my first principal component. But let's say that the data is not embedded in 2 dimensions, but perhaps in 3 dimensions. Then I need to look for more than just the first principal component. So to do that, I could subtract Yeah, go ahead. Yeah. Is there a reason why I take the largest eigenvalue? So I wanted to maximize this thing, and the only admissible solutions, or the only candidate solutions, must fulfill this eigenproblem. But I wanted to maximize the whole thing, and the Rayleigh ÄìRitz theorem tells me that the largest possible value I can get will be the one, so will be the eigenvector pertaining to the largest eigenvalue. You also see it in the above equation here, because we say that the norm of W is 1. So and x transpose W is the same as lambda times W. So in other words, we want to find the biggest lambda, the biggest eigenvalue. Okay, now to find the next few principal components, I can go ahead and subtract the already found principal components from X, and then do the same computation that we just did. It's not how you would do it in real life, but conceptually you can go about it as follows. So you can say that xk is x minus and now these are rank 1 approximations to x that I subtract. So this thing here was the coordinate in the new basis. Sorry, the coordinates in the new basis. They are also called the scores. And these were the principal components. Which are also called loadings. These are the vectors of the new basis. And this here is an outer product between one vector and another vector. So overall, this whole thing is a rank 1 entity. And I now subtract a number of rank 1 approximations in terms of the first, second, third, and so on principal component from my original data matrix. And I'm only writing this down conceptual, because in practice you would use the singular value decomposition that we talk about later on. And if your problem fits into memory, and then you're getting all the solutions at the same time. No need to iterate. Okay, now all of that was a means to maximize the variance within the subspace. And equivalently, we can look at the residuals and minimize these. So I can say that the direction that I'm looking for is a minimizer. Again, I'm looking only for the direction. I want to restrict this vector to unit length. And now the residuals I can express as follows. X is my original matrix of observations. Minus so I'm explaining all of this in detail. W transpose times X, these are the scores. These are the coordinates in the new basis. And if I multiply them with the basis vectors, I obtain an approximation to the original observation. So this is a matrix, a P by N matrix, and that is a P by N matrix. And I'm interested in all the sums of the squared columns. But if I'm summing over all squared columns, I can simply take the sum over all squared elements of the entire matrix. And this is what this F says. So F is a Frobenius norm. If I have any matrix A, and I take the squared Frobenius norm, means that I'm summing over rows and columns of the squared matrix elements. And another way of writing this is in terms of the trace. So the Frobenius norms, operationally, it simply means square your matrix element-wise and sum over all these squared elements. All right, and I'm coming back to my calculation here and saying that I want to minimize the squared Frobenius norm of this. I'm now using this form that I can rewrite this as the trace of the argument transposed times the argument. So I get x transpose x minus x transpose, here the second part, so I've been multiplying out the whole thing. Still under the condition that the norm of W be 1. And because of that, this is a scalar 1, which I can omit. And the first term does not depend on W at all. It's independent of W, so I can ignore it for the purposes of this minimization. And I can rewrite this as and because the trace is invariant under cyclic permutation, I can say this is the same as W transpose X, X transpose W, which is now, if you look at the dimensionalities, this was 1 by P, P by N by P, and P by 1. So the whole thing here is a 1 by 1 matrix. Overall, this is 1 by 1 or a scalar, and the trace of a scalar is just the scalar itself. Which allows me to omit the trace operator. Okay, now I'm going back to the other formula that we had when we were trying to maximize the variance. So on the previous slide, we had said that we want to compute the maximum of W transpose X, X transpose W, subject to this constraint of the length on the vector of 1. And now, instead of the maximization, I have a minimization with a minus, which is the very same thing. So in other words, this is the same, or this must have the same optimum as that. And this is why these formulations are equivalent. They are sometimes also called the synthesis and the analysis view of Pca, and they are equivalent. Now I've argued here in terms of doing this for the first principal component and then for the second and then for the third and so on. In real life, you would simply diagonalize this matrix x transpose a single time and then find that your basis vectors, your principal components, are given by the sorted eigenvectors and the scaling factors are given by the square roots of the eigenvalues. You have a question? Oh, yes. So if you change the norm in your objective function, you simply obtain a different method altogether. So you're talking about us using the Frobenius norm here, yeah, which is the simplest thing you can do mathematically. Quite a valid alternative would be, for instance, to say that you don't want the Frobenius norm squared, but you simply want the L1 norm. So you want the sum of the absolute deviations to be as small as possible. And that's a valid question, and it's the same thing in regression, where the kind of linear regression that we typically use implies this squared norm, and then there are the alternative exists. It is called, I believe, Laplace regression, but it's simply harder numerically. That's not so much of a problem in times of computers, but the optimization becomes harder. Yes, exactly. Frobenius norm this is the L2 norm for matrices. More questions? Okay, so let's look at a few examples of this. So, what can you do? For example, produce a so-called scree plot. I'm not sure where this name comes from, but what it means is that you plot the eigenvalues, or some people plot the square root of the eigenvalues. And here you see, for instance, for these MNIST digits, how they decay as you go to higher numbers. And if you take the eigenvalues themselves, they tell you how much of the variance of your data you recover in the first few dimensions. So on the right-hand side, I've shown the cumulative sum over all of the 768 eigenvalues, and you see that once you go up to 300 or so, you have really recovered all of, or virtually all of, your variance. In other words, you could reconstruct your digits exactly, or practically exactly, by not using 768 numbers for each of these patches, but by using only the first 300 numbers. If you are willing to ignore, the very fine details that are still left in these higher components. But you can also be more extreme. You can say, I simply want to afford 20 numbers for each digit, and how much does that buy me? And then you can read off that this will give you 80% or so of your variance. Now, for things like digits, we can also really look at these errors. So down here's an example of 10 concrete digits. This is the mean of all of these digits, which had to be subtracted. And then you see up here the principal components, which have now been plotted as images. And you see that these principal components, they're not so easy to understand in general, because they are linear combinations of all of your features. So if such a linear component, if such a principal component has a zero entry somewhere, it means that it does not depend on the feature. But you see that here, these are not very sparse, okay? And well, we can look at them and say that perhaps this component tells me if this is a 3 or not a 3, that it has some of this information. But generally speaking, there's no easy interpretation. And down here you see the approximation to these 10 concrete numbers. If you use just, for example, just the first principal component, and well, that's not a very good approximation, they are pretty much the same. This is the first and the second component, first and third, well, and I think you need of the order of 10 or even more principal components to come to a reasonable approximation. You see that, for example, this digit here, I think overall I've plotted, I've used up to 20 dimensions here, and this digit really was lying pretty well in this 20-dimensional subspace. So the residual to this subspace was relatively low. I can recognize that this is a 6. But this one here, for example, it was lying, it has a large orthogonal component. So this was, I need more than 20 components to reconstruct this figure well. And this plot here is a summary of for the entire data set. And if you, well, the scale is too small for you to read, but this is 100, this is 200. So you need 100 components to get to 90% variance or so, and not just 10. You have a question? I should have said eigenvectors and the principal components. The scree plot itself consists of eigenvalues. So I'm writing this down explicitly. These are the numbers 1, 2, 3, and so on. And this is the magnitude of the eigenvalue. And in the ideal world, it would look something like this. So you would have large first and second eigenvalue, and then pretty smaller, higher eigenvalues, which means that by just looking at a 2D plot of your data, you will get a fair idea of what it looks like. So the scree plot is a plot of the sorted eigenvalues. And it gives a conservative estimate of the intrinsic dimensionality. It is conservative in the following sense. If I have data like that, we would say that, as humans, we would say that the data is locally one-dimensional because I can fit a pretty nice curve to this data, which is a one-dimensional curve. But when we do PCA, we're looking at all of these points at the same time, and you see that we need, we do have some spread in the first and the second principal component here. So that's why it's a conservative estimate. And secondly, maybe estimate is even an exaggerated word. Maybe I should have said it gives an impression of the intrinsic dimensionality, because I will take a plot with more eigenvalues. In the ideal world, you would have the first two, which are very large, and then the rest being very small, and then you would say, okay, the intrinsic dimensionality here is 2. Unfortunately, in practice, so you're looking for, these are called shoulders, or this would be a shoulder after the third eigenvalue. The first 3 are very large, and the remainder is small. In practice, however, you typically find something that looks more or less like an exponential decay, and it's not clear if you're looking at a plot like this. Do you call your data 3-dimensional or 4-dimensional or 5-dimensional? It doesn't really tell you. Well, and it simply reflects the truth that the intrinsic dimensionality is lower than the nominal one, but there's no guarantee that the data fits or uses, let's say, there's no guarantee that data is uniformly distributed with the same spread just along the first 3 principal components. And then, by the way, you can do some theory here. Let's say that if really you have 3 components in your data, and the rest is just isotropic noise, you will not find the following. So naively, you would perhaps expect that you get 3 large eigenvalues, and then if you have isotropic noise, the rest would be just the same. This is true in the limit of using infinite number of observations, but in practice, where you have a finite number of observations, your data always looks like it has some preferred orientation. So let's say, so to give you a cartoon of the situation, I'm using 2D data from an isotropic normal distribution. So the density of this distribution looks like that, but I'm just picking 2 samples, and let's say I'm getting 1 sample here and 1 sample there, and now it looks like your data is oriented, doesn't it? Yeah, in this direction here. And well, you would tell me with 2 points you cannot estimate 2D covariance matrix. That's entirely correct. But this is a sketch of what is often going on in higher dimensions. You have too few points in too many dimensions, and you cannot naively estimate a covariance matrix. So here, if we estimate the covariance matrix from these 2 points, we will see a lot of structure which is not really there. And that's the same in higher dimensions. So even if you have isotropic noise, it does not give you eigenvalues of equal size, but you will find some pseudo-orientation and get this kind of decay here. And then you can do some theory and see if your decay pattern here fits an isotropic noise or not, if there's really some more structure in the data, and so on. Okay, so what are applications? You can use discrete plot, or you can use so-called score plots. This is what you have already seen before. A score plot is just a scatter plot of your data. In terms of the first principal components. Any questions? Go ahead. What's the difference between PCA and orthogonal matching pursuit? Yeah, so PCA has many names, and one of the more famous ones is orthogonal proper decomposition. But orthogonal matching pursuit, I believe, is a procedure where you're looking for interesting projections of your data. So where you look for projections where they appear non-normal. Is that correct?
I thought it was very similar. I don't really remember what it was.
So I think Bernhard is Googling for this. So other names for PCA include orthogonal proper decomposition, or some people call this the Kahunen-Loewe transform. And Bernhard, what can you tell us about? Nothing. Okay. So we'll do this offline. After the break. Thanks. Which I'm not going to do in formulas, but just in words. We will see some of them in formula later on. We still have a frame there, Bernhard, on the screen. There is, on the one hand, Hebbian Learning of Pca. So Pca was also reinvented or described by the neural network people, and we will discuss this algorithm when we talk about neural networks, which will be quite soon. And this gives an iterative estimate of only the first principal components. And that's useful because you do not always need, if you're interested in compression, then you don't need all principal components. And if you just want the first few, and if you have a very large data set, then these algorithms may make sense. Then there is Kernel Pca, which is very closely related to multidimensional scaling, and I will talk about it again when we come to multidimensional scaling. This is used to approximate data that lies on nonlinear manifolds, so when these linear subspaces don't work well. There is robust Pca that is not so susceptible to outliers. There is sparse Pca, which I'm going to mention again later today, which has basis functions that are linear combinations of a subset of all features only. And there is probabilistic Pca, which, as the name implies, is a probabilistic variant. The Pca, as we have discussed it, didn't make any mention of random variables and distributions and so on. And when you assume that you have noise, additive noise on your data, and you can say something about the distribution of this noise, then probabilistic Pca is for you. So this can exploit some prior knowledge that you have on the noise structure. In the estimation of your scores. Okay, I'll stick with the other screen. I wanted to give a demo, but I should test that first. Let's do that after the next break. Okay, so that much about Pca, and I now want to talk about the singular value decomposition. Or SVD, which is a tool from linear algebra that is used a lot nowadays. So if you read research papers, then very often the linear algebra part of it, or some linear algebra part of it, is formulated in terms of the SVD. So in general, if we have a matrix with m rows and n columns, then the SVD of A is given by USV transpose. And now all of these things have names. So V is a matrix that's holding the so-called right singular vectors. U is a matrix holding the left singular vectors. And these are related to the range and to the row space of the image. And S is a diagonal matrix, and it holds the so-called singular values. And U and V are orthogonal. So U transpose U is the identity matrix, and V transpose V is the identity matrix of a different dimension. And this matrix S, which is also called sometimes sigma, and that's important that these are ordered. Because in languages like MATLAB, if you use an eigendecomposition, the eigenvalues that come out are not necessarily ordered, but that's part of the definition. In the SVD, the singular values must always be ordered. And they're all non-negative. Now, a couple of useful facts. Firstly, every matrix has a singular value decomposition. And one can prove that the singular values are uniquely determined. And if the sigma I or the Si, if the singular values are distinct, so that is, if there's no degeneracy, then also U and V, the left and right singular vectors, are uniquely determined. The SVD is sometimes used to estimate the rank of a matrix. So the rank of a matrix A is the same as the number of non-zero singular values. And that is because I can write my matrix A in terms of rank 1 components. So this is the ith left and right singular vector, and that is the ith singular value. And this is an outer product which has rank 1. And well, if I add 5 of these components up, then I have a rank 5 matrix. And if you want to estimate the rank of a matrix, then the case is often that you have some notable singular values and then others that are really practically 0, but not quite. So only up to numerical accuracy. And then you so MATLAB, for instance, has some inbuilt threshold, what it still considers numerical inaccuracy and what a real difference. So here, for instance, you would say that the rank of this matrix is 3, even if there are some tiny numbers left out there. This is useful, for example, in image analysis. If you have a convolution operator, so if you have a mask and you want to find out if the mask is separable, then you can use the SVD to decompose it or to rewrite this operator, and ideally you will find that your operator is separable, in which case you can write it as an outer product, and that means instead of a 2D convolution, you simply need to convolve with a 1D operator along the columns and the rows of your image, which makes for huge savings. So that was the rank. Then if you need to compute the Frobenius norm, so further properties of the SVD, if you compute the Frobenius norm of your matrix, then you can use this formulation with, sorry, not this, well, I'm taking the square here. Then you can use this formulation with the trace. Which will give you V S transpose U transpose U S V transpose. And U was to be orthogonal, so this is the same as the trace of V S as V transpose. It's S is diagonal, so it doesn't matter if I transpose here or not. And then I can permute and write this as trace of V transpose V S squared. And again, V is orthogonal, so this is the trace of S squared, or the sum of the squared singular values. So what I wanted to get to was this thing here. The Frobenius norm of the matrix is given by the sum of the squared singular values. Then for similar reasons, the determinant of A is the product of all your singular values. And I will now make a plot of this and then show you that or why the SVD or truncated SVD can be used for matrix approximation. So first a picture. using a matrix X here holding all the data. And I can decompose that exactly in terms of a matrix U and a matrix S. I'm now drawing a form that's not so typically used, and V. So let's look at the dimensions. I had said that X was, or perhaps I should use A because we've been writing A all along. Let's say A was m by n, then U is m by m, S is m by n, and V is n by n. And this thing is called the full SVD. Now let's look again at the structure. S is a diagonal matrix, so it has the singular values here, zeros there, and zeros here, which is not so interesting. So I can leave away all these parts corresponding to the zeros, and I then obtain the reduced SVD. Let's take a more distinct color here. So the reduced SVD here has m by m and m by m, and here m by n. So for the reduced SVD, I'm keeping only the red blocks here. And that is still exact. And if I now want to approximate my matrix, I can go ahead and truncate it. So this will give me the truncated SVD. And I can then, for instance, stick with just the first few singular values, let's say with the R first values, and set the others to 0. So let's say these are the R first singular values. So dimensions here would be m by r, r by r, and r by n. Sorry, this is transposed. Okay, and for those who know so if I have a matrix of a rank that is smaller than the number of rows or columns, then you can attach names to all of these parts. So you would say that this part here spans the row image or the row space of the matrix A, and the row space, some people call it the co-image. Note these only if you have heard of these terms before. The rest would be the null space, and that part is the left null space, and this part here would span the range of the matrix A, or that's sometimes also called the column space. Okay, and in languages like MATLAB, you can indeed give a flag and tell the machine if you want the full or the reduced SVD. Now this truncation actually has a deeper sense, and that's proven in the following theorem by Eckart and Young. Are you finished painting? Yeah? No? Okay. My conclusion is that writing on paper is faster than on iPad. So the Eckart-Young theorem for matrix approximation it states that a truncated matrix is the best approximation to the original matrix that you can possibly get in terms of the Frobenius norm. So it states that the best matrix approximation, where best is measured by the Frobenius norm, is given by a truncated SVD, truncated singular value decomposition. And I'm giving you the sketch of the proof here, which runs as follows. I'm given some original matrix A. So this is the original. And I want to approximate it with a matrix A tilde. So as to minimize the squared Frobenius norm under the constraint that A tilde cannot just be any matrix, but the rank von A tilde should be R or less. Now I'm replacing, so I want to minimize this thing over R tilde, where R tilde fulfills the condition of having rank R. Now I'm rewriting this by replacing A with its SVD. So this thing here is identical to A. And I'm now exploiting the fact that the Frobenius norm is invariant under unitary transformations. So I multiply, and you can check that by using this argument or this formulation in terms of the trace. So I am multiplying this from the left with U transpose. Is there a question? No. And U transpose U will disappear. So I have S V transpose minus U transpose A tilde. And I can similarly multiply from the right with V. Which will give me S minus U transpose A tilde V. And I'm now finally also expressing A tilde in terms of its SVD. So I will say A tilde is U tilde S tilde V tilde transposed. Okay. And I know by definition that this comes from an SVD. So this thing is diagonal. And I also know from its definition that this thing here is diagonal. So in other words, I have a matrix S which is all 0 except on the diagonal. And if you remember the definition of the Frobenius norm, or the squared Frobenius norm, it means that I take all matrix elements and square them and sum them up. So I have a good reason to make this entire second matrix also diagonal. Because if it isn't, then this will inflate my Frobenius norm. So I'm putting this down in words to avoid contributions to the Frobenius norm from off-diagonal elements. I want to make this entire second term also diagonal. So this is U transpose U tilde S tilde V tilde transpose V, this entire second term. Should also be diagonal. Well, and to guarantee that it does become diagonal, again, knowing that S tilde already is diagonal, I can assure that by saying that U transpose U tilde should be the identity matrix, or in other words, U tilde should be U, and by the same argument, V tilde should be V. So if I take the SVD of my approximate matrix, I can avoid contributions from off-diagonal terms by assuring that the left and right singular vectors are identical to those of the original matrix. Now the only thing remaining is to see what happens with the singular values. So I'm left now with a minimization over S tilde only. And subject to the constraint that this should be only of rank R. So if I'm now looking at this matrix explicitly, so I have S1 minus S1 tilde and S2 minus S2 tilde and so on. And from this matrix here, I want to take the Frobenius norm squared. Given that this matrix should be of rank R, only R of these S tilde values can be non-zero. And remember now that these are sorted. So S1, I know that S1 is at least as big as S2, which is at least as big as S3, and so on. So if I now want to have an approximation of only rank R, what should I be doing? Exactly. So if I want to minimize this, it is best to take only the R largest singular values in S tilde. Oh, sorry, this is very low. So the summary is, if I want to approximate A, with a SVD as follows. Where S tilde is a diagonal matrix holding the R largest singular values, followed by zeros. Okay, and then that gives me the best approximation in terms of the Frobenius norm to this original matrix A. So we've talked about the SVD. Any questions so far? Then I can ask how this relates to the principal components analysis that we had just seen. So what's the relation between the SVD and the PCA? For the PCA, we wanted to diagonalize XX transpose. And because of the orthogonality, I can rewrite this as U S squared U transpose. And this is diagonal here. So in other words, the left singular vectors of X are the eigenvectors of the scatter matrix XX transpose. Now I can also build another matrix. So this was the dimensionality here of this entire thing was P by P. I can also build another thing, namely X transpose X, which will be of dimensionality n by n. Okay, and if you write it out for yourself, you find that this is V S squared V transpose, which says that the right singular vectors of X are the eigenvectors of this matrix X transpose X. And as these formulas show, so this S squared is the same as that S squared. One of them will have a larger dimensionality than the other, but the singular value, the non-zero singular values are the same. So in both cases, the eigenvalues of XX transpose and X transpose X are the same, and they are given by the square of the singular values. So the eigenvalue of the scatter matrix is related to the variance, or it gives you the variance, and the singular value is the square root thereof, so it's like the standard deviation. And if you now want to do the PCA in the real world, if you want to compute only the first few eigenvectors, then you should use an iterative approach. If you want to compute all, then the recommendation is actually to use the SVD for that, because it is numerically more stable than first building the scatter matrix and then diagonalizing that. And by the way, it matters, at least in an older implementation that I have, it matters if you compute the SVD of X or the SVD of X transpose. So you might want to try out if it makes a difference for you, because sometimes P and N are very different. So it might make sense to try out which one is faster. Okay, and there's one relation between the X and the SVD, and just for completeness, there's another relation. So if you build a matrix as follows, if you take 0x, X transpose 0, and if you stack the left and right singular vectors, this time with no transpose here, you can rewrite this in terms of its SVD. And if you now multiply that, you will find that, well, this contribution gives 0 plus that will give you US, and this contribution gives you VS plus 0. So that's the same as UV times S. And more relations that could be useful, more relations like this can be found in a paper by B and Cristignani and Rosipal, and this is called Eigenproblems in pattern recognition. Any questions? Go ahead. How is it used? So the SVD, you mean? Okay. It is in general used if you want to speed up your linear algebra and you're willing to make a lossy approximation. So simply to obtain a lower rank approximation to your original matrix, whatever it is. Now, in our case, this is what you use if you want to perform principal component analysis. It's a bit trickier with pictures, and this is what you will do in the exercises, because let's say you have a collection of pictures, and how do these pictures now relate to all these matrices that I've shown? The pictures themselves are not one of the matrices. Each of the pictures needs to be vectorized. So if I vectorize these pictures, I obtain my matrix X, which has P features and N observations. And this, so if these are images here, then P would be the number of pixels in any single one of them. Okay, now here's your matrix X, and you want to now perform a principal component analysis. Now what you do is, in the language of your choice, you write that, and now depending on your syntax, you know that 3 things are coming out, so you need to assign them to differently named matrices. So there's your principal component analysis in a single line. Okay, what I've omitted here is the subtracting the mean. Okay, but you know, people have been making a living out of selling software for principal component analysis. Okay. Yeah, S is these. If you take the square of these values, you will find the spread along individual dimensions. So now let's say for PCA in particular, I want the basis to be orthonormal. So I had previously called this the matrix W, or we had talked about vectors more precisely. Let's see, I said that I think I wrote W transpose X. Yeah? So W itself was always a p-dimensional vector. So W transpose would be U. This would be the I have to think if I have to transpose here or not. What did I use? I wrote W transpose X, didn't I? Okay. So W, the small W transpose, the scalar one, had a dimensionality of 1 by P. And now I want altogether R of them. Yeah? So I would take, I now want a matrix W which is R by P. And I'm now calling this, I'm not sure if it's a matter of convention. But anyway, this is this thing is R by P. These will be the principal components. I'm really confused about the transpose now. So X equals U as V transpose. And I want U to be my basis, and I want SV transpose together to be the scores. And previously I had never written a matrix capital W, so I'm not sure if I should, what's easier now, to put a T or not. Okay, but if I am, my original matrix X was P by N, and if I want to truncate now to the first principal components, then I will here use only the first R columns, and here only the first R rows. So the first columns of U are the principal components. And the first R columns of U are the R principal components, and the first R rows of SV transpose are the scores. Hold on, are the scores for each observation. The scores for the images would be their coordinates in a scatter plot. So these are the scores. You cannot directly, you see, I can approximate a patch with, let's say, with 2 numbers in the extreme case, as has been done here. And that does not look like an image any longer. The only thing that looks like an image is if you now multiply the scores with the loadings. If you multiply your coefficients with your basis functions, then you get things that look like an image, maybe like a bad image, but still like an image. Okay. And I think a bonus exercise is to do this on faces. And, 15, 20 years ago, this was the forefront of research, where people found out that, that was in the early 90s, that you could use principal component analysis not just on chemometric data, but also on images. And in this example here, you see on the left-hand side the basis vectors, and you can vaguely interpret them as, for instance, here wider head or narrower head. Here you have a small shift left-right, you see, because I have some positive numbers here and some, well, actually some negative numbers on the top. So let's say it's a diagonal shift, which is encoded by this principal component. Here's a left-right shift. One of these will probably encode for people wearing glasses or not. Yeah? But in general, you see that the features or these basis functions are redundant in the sense that you tend to see the same structure in many basis functions just with different sign, which is a bad thing, at least if you want to interpret these. And that was the motivation for coming up with advanced methods that give basis functions that are more complementary to each other. And then on the right-hand side is an approximation of a phase which looks roughly like that in terms of more and more principal components. So for this particular data set, here's your average phase, and then here's your average phase plus the first and second, plus first, second, third, and so on. So you add more and more principal components until you get an approximation of this image. Let's say this image is, if it's 100 by 100 pixels, this would be 10,000 numbers. And using that kind of technique, you can get an approximation of this image with only perhaps 60 numbers or 100 numbers instead of 100,000. So this is this dimension reduction. On the one hand, it helps speed up all of your computations, but it can also, especially if the images are noisy, it can actually improve recognition rates also. Yes, to reconstruct, you need both your basis and the coefficients. Yeah. Yeah. From all the faces in the database. Yes. Exactly. Okay. I have a movie which at least looks nice. I'm not sure if it, if you understand things better by looking at it. But here we're looking at satellite data from the local Institute of Environmental Physics. It's not the raw satellite data, but instead people have computed from the raw data the NOx concentrations. So nitric oxide concentration in the atmosphere and color-coded. Red meaning lots, like you see here, the heavily industrialized areas of China, Central Europe, here around the Great Lakes. And then there's some coal power plants, I think in Australia here, or some mining going on there, which leads to increased NOx rates, some in South Africa, and so on. So this is now a single picture which has many thousand, or you require many thousand values, namely the value at each pixel, to describe this picture. On top you see the scree plot, which shows you that in this particular data set here, you really have two principal components that are much more influential than all the rest. So here you can capture a fair part of the variance by simply projecting your data on the first two principal components. And this is what I've done on the right-hand side. So we now get satellite images that are acquired roughly once a week. And each image now becomes, in this score plot, just a single dot. And the structure in this plot, well, this is what was in the data. I didn't put this in. So let's see if we have a viewer somewhere. Let me try again. Okay. So this is now over time, and you see some huge variations which have to do really with the yearly effects. So summer and winter, and that impacts the NOx distribution in the worldwide atmosphere. And the currently shown image is always indicated here as a red dot. And well, out comes a circle, and this is a very pictographic summary of the the yearly circle of things in our planet. So after waiting for 1 year, you expect to end up in a similar position as you were in 1 year before. And well, this kind of plot can now be interesting if you see a point lying further from all the others, then that would be a particular datum where you would want to look at the original image and see if something special was happening. Eigenvector, first principal component, second principal component. Okay, and these are just the scores or the coefficients in this new basis. Any other questions? Go ahead. So an entire image like this, I simply said these are, I forget how many pixels it is. I simply said these are 10,000 measurements, and I put them into a vector, ignoring that this is really an image. And so all of this became a single column of my matrix X. And it's just important that you use the same ordering each time, but the ordering itself of the pixels was arbitrary. And then the second dimension, so the number of observations, that was time. And of course, if you deal with images, then you can think about really exploiting the fact that this data has spatial context. And if the data was very noisy, for instance, you could put in smoothness priors in the spatial domain. But all of this was ignored here. It was just pretend, all of these images were simply looked at as vectors of measurements and processed as such. How long does it take to compute? A couple of seconds. So, but here, in particular, you see this is so one dimension. So here P is, if it's 10,000 measurements, then the matrix has 10,000 rows, but there were only 600 or 1,000. I forget exactly how many measurements. So if you want to perform Pca here by diagonalizing the scatter matrix, it really matters if you diagonalize x transpose or x transpose x. At least if you use normal implementations that don't check the structure of the matrices for themselves. So you want to use the smaller one. And via these equations for the SVD, once you have computed, for instance, so you have x equals USV. Let's say if you have S and V and you're looking for U, then you would right multiply with V and with S to the minus 1 to solve for U. Okay, so for example, I would find that U equals, so I've right multiplied X with V, and I've right multiplied with S to the minus 1, which is trivial to invert, and then you get U out by this equation here, if you know the right singular vectors and the singular values. And X was your data matrix. Any more questions? Go ahead. Can you show it again, please? Okay. I've broken my own rule of always annotating all x's, so sorry. So we're looking at this picture here, yeah? The principal components are simply a basis. So principal component analysis, you can look at it in terms of translating and rotating your original basis. you translate it such that your new basis has its origin at the center of mass of your observations, and then you rotate it such that your data has maximal spread in this new basis. And your new basis vectors are, they are somehow, or they lie somehow in the original basis. So in particular, the new basis vectors can be linear combinations of all the old basis vectors. And in this new basis, I now have, let's say, over time, I have 1,000 images over time. And I can now simply plot the position in the new basis of each of these 1,000 measurements. So there is no time in here. Time is only implicit because I show the images one after the other, and I show those dots one after the other. So first principal component, second principal component, and then these are the coefficients in terms of the new basis, also called scores. And I think I might have images of the, here actually I have the two principal components, or the basis vectors also. This one is the mean, which was subtracted from the data. And again, you see, all year round which places are the most dominant producers of NOx. And then there are these two basis vectors, here again shown as images. But the principal component analysis in itself did not know that these are images. I have just vectorized things, did PCA, and then I have unvectorized them to show them as images again. And well, if I want to interpret this, then I would say, you see, I have some large values here and large negative values there. So the first principal component would describe the yearly variation. And this one here, it has low values here and high values there. So this one tells me if I have more activity in the northern or in the southern hemisphere. And I can interpret this as a seasonal effect also, because, well, I know over how much time the satellite movies were acquired, and this really corresponded to a year each time. So my interpretation of this is that in winter, in our winter, these people need to heat less, and in our summer, they need to heat more. So I think this is another seasonal component which is orthogonal to that one here. No, these components are all orthogonal, but that doesn't say anything about independence of the data. I had made a plot when I talked about the intrinsic dimensionality. So if you look at this example here, these observations are by no means independent. You see, I clearly have some structure here, but if I fit principal components to them, I will find that, first center of mass perhaps lies here, and then I will find that this is first principal component, and that is the second principal component. And these are all orthonormal vectors, but in the length of these axes, I have already implied, how much scatter I have in the different dimensions. But so I would fit this with a 2D plane. It doesn't make any statement about independence or not. There is a different technique, independent component analysis, which capitalizes on just that, on the original sources being assumed independent, and then one looks for a rotation of the data that brings out the original independent measurements. The variance, yeah. So the principal components are just an orthonormal basis, and I have drawn one axis longer than the other just for psychological reasons. Really, the variance goes or is expressed in terms of the squared singular values or in terms of the eigenvalues of the scatter matrix. These questions are very good because I think they will help a lot for the exercises. So as image processing people, I think we have more difficulty with principal component analysis than others because others just have a matrix full of data. But for us, we have images which are already matrices. And in between, there's this vectorization operation that must not be forgotten. More questions? Okay, you can think of more in the break.